Good afternoon. My name is Don Scott. The hypothesis of the so-called electric sun. The electric sun is a sort of a natural outgrowth of the electrical universe hypothesis. We've already discussed the idea that there are indeed in the arms of our galaxy these electric currents. We know that there are magnetic fields, and we think we know that the pinch effect of the electric currents that we are pretty sure are there throughout the universe really is what creates galaxies, and within those galaxies create the stars that constitute the galaxies. It's only a slight increment beyond that to think that if the electric currents actually coalesce the stars through the pinch effect, that why shouldn't those electric currents continue and power the star? At least consider that possibility. The pioneers of this idea, obviously Immanuel Velikovsky, Ralph Jurgens, who was an engineer, was the person who really put this hypothesis together. After his death, Earl Milton carried it on. Wal Thornhill, of course, and your humble servant, to whatever extent I can, are sort of the proponents of it now. There was also, I left persons off that list that should be on there, and that is Hannes Alfvén, who in his paper in 1986, in that what I consider to be seminal paper in the IEEE proceedings on plasma science, actually had a circuit that showed the electric sun. It's slightly different from the one that Jurgens and Wal and I think is appropriate, but he was there in 1986. What I'd like to do today is to show some of the problems of the so-called standard model. That word model should be plural, models, because for every thing that we see, every phenomenon that we see in the sun, there seems to be a new model, or at least another patch on the previous existing model. And I'll discuss just a few of those problems that I feel at least are fatal, absolutely fatal for the models that are so-called accepted these days. And I would like to then demonstrate how precisely those problems are no problem at all for the electrical sun model. Twisty things in the solar wind, I should say, are Birkeland currents in the solar current. The basic idea of the standard model is that the sun and every other star, the sun being just sort of a medium Metz kind of star, is powered from within by a thermonuclear fusion reaction. That's the hydrogen bomb type reaction. Heat energy is delivered from the core to the surface by so-called non-stationary convection. I haven't figured out yet what non-stationary convection is. I know what convection is. A sort of a mysterious convection. It's radiated there into space. And gravitational and magnetic fields are, of course, as in all things, astronomical important, but let's ignore electric fields. That's the standard model. Eddington was the one who really said and rejected the idea that the sun could ever be powered from without. He considered the fact that there were not enough meteors flying through space to impact it and power it that way, and he just sort of forgot about the fact that electric currents were present. If you look down, this is a classic example that I think is appropriate. Wal, I think, was the one who came up with it. If you look down from a spaceship on the Earth at night and look at San Francisco and New York, you must think that there's a tremendous amount of energy being produced in San Francisco and New York and all of these cities that glow. And of course, there's no energy being produced there. The energy is being produced in hydroelectric plants hundreds and hundreds of miles away, delivered invisibly to where that energy is being liberated. I maintain that's exactly what's happening with the sun. The problems, the ones at least that I'd like to talk about this afternoon, the big problem, the famous problem, is the missing neutrinos. And talk about that in a second. The idea of this heat transport from the core to the surface, if indeed the heat is made in the core from the so-called fusion reaction, how is it transported to the core? Is it reasonable to say there's convection occurring there? The idea of convection, the granules that we see on the photosphere are supposedly the top of these convection columns. We'll discuss that. There are some oscillations in the sun's size and brightness, and of course oscillations in the solar wind, as somebody pointed out the other day. If there's a fusion reaction going on in the core, then how can does this reaction, does it have periodicities? That's never been discussed by nuclear physicists. There is actually a temperature minimum in the chromosphere. Where in the world does that come from? If the heat is all generated at the core, the temperature should get lower and lower and lower the further away you get from this thing. All of a sudden you find there's a minimum and then the temperature increases. Totally inexplicable in light of the present standard so-called model or models. The solar wind actually accelerates. It goes faster and faster and faster. How can you generate the stuff at a point and then spew it out and not have the stuff, whatever it is, the particles in the solar wind go slower and slower and slower? Why do they accelerate? And there's other problems as well. Well, let's just talk about a couple of them. The missing neutrinos. I'm not a nuclear physicist, but generally that slide shows you that if you take 4 hydrogen atoms and combine them, you combine 2 of them and you get deuterium, and put on another one, you get tritium, and there's about a 3-stage process. And you get, at the end of it, a helium atom, and you get lots of energy, and you also get a flow of neutrinos. You got to have those neutrinos, because if you don't get those neutrinos, that reaction isn't going to happen. And people have been looking for that flow of neutrinos for about 40 years now. They found, some people say 1/3 of the number that they should find. Some people say 2/3. Some people 1/2. But nowhere near the amount of neutrinos that would be necessary, that we would observe, if indeed the core was a fusion reaction and if all the heat is being generated at the core. So what does modern astronomy do? Is this enough to make them go back and reconsider? Maybe we don't, maybe Eddington wasn't right. Maybe we should relook this and see if there's some other source of energy. Of course not. No, we've adopted this model. It's sacrosanct. We can't go back and look at that. So instead, we're now going to challenge the neutrinos. There's something wrong with the neutrinos, that we don't see them. And the latest, believe it or not, is that somebody has postulated that neutrinos come in different flavors, some of which are invisible. Never go back and challenge your basic assumptions. Just, shoot the messenger. The heat transport problem. Convection in the Reynolds number is a number. Fluid dynamicists have these numbers that describe flow, and you can calculate this Reynolds number based on the viscosity and the temperature and the density and mobility and all sorts of things. And it's a witch's brew of things that we can tell about the sun. And it turns out that the Reynolds number for the sun, at least near the surface, is not just a few times, but it's 100 billion times too big for convection to occur. Does this slow them down? Not a bit. They just ignore it, keep on. Jurgens said that photospheric granulation is explainable in terms of convection only if we disregard what we know about convection. But that's still the accepted theory. The oscillations in size and brightness. There's a 27-day, 43-minute periodicity in the solar wind. In fact, the other day we said it increased to unknown or unseen levels. But there is this periodicity. If it's periodic, how can that periodicity, how can that fluctuation be produced by something that's way at the center of the sun and then being radiated through convection, which is a smooth process, to the outside? What makes this 27-day period? How can that fluctuation occur like that? There's nothing in the standard model to produce that. The solar brightness oscillation, if you think 27 days is bad, the sun actually oscillates in brightness from a few minutes to near an hour. So the thing is pulsating very rapidly. There's no way in this world, that in this solar system, that could happen. And the third one is, to me, astounding if you haven't heard about it. That is, there's an expansion and contraction of the sun in the size of the sun. The thing actually bulges and fluctuates in size like a balloon. And the extent of that bulging is 10 kilometers. And that happens at about a period of about 160 minutes. Where did that come from? And how do you explain it from the so-called standard model? They just ignore it. Here's the temperature minimum. This is a profile. The horizontal distance is, as you can see there, height above the convection zone in kilometers. And so one would expect that you should start out at some temperature at the surface of the sun. This point on the left here is the surface of the sun. You would expect this to decay and decay and decay and decay and decay, maybe 1 over r squared, whatever, the way a normal black body would radiate. The further away you get from a wood stove, the cooler it gets. Well, all of a sudden, this is about 6,000 Kelvin. There's a minimum somewhere in here. Exactly where this minimum occurs is sort of a matter of conjecture, but it does occur. And then all of a sudden in this so-called transition region, whammo, this is not a linear axis. This is a logarithmic axis. The temperature jumps from a minimum of about 6,000 to 1 million or 2 million Kelvin. How? If all the heat is generated at the center, how in the heck do you secrete it out to here and then all of a sudden let it go way out here beyond the surface of the sun? No answer, but no reconsideration of the theory. The solar wind speeds up, it accelerates. As we travel radially outward from the base of the corona, the particles, the positive ions that make up the solar wind, increase in velocity, they accelerate. There's nothing in the standard model that predicts that, nothing. Here's a picture of how it happens. It isn't just a mild acceleration, it's a whooper of an acceleration. The particles, the velocity at the surface of the sun are quite low. By the time you get out to Mercury, the various ions have sped up. By the time you get to Venus, they've sped up further. By the time you get out to us, you're traveling the orders of millions of miles an hour. So these things are really getting a kick. This is quite a sports car. How does it accelerate? Why does it accelerate? If indeed all the energy comes from the center of the sun. Well, here's the basis of the electric sun model. We maintain that the sun is actually powered not from the inside but from the outside by a flow of electric charge, that is, electric current, from its galactic environment. The sun is a uniformly dense sphere of gas. There may be something at the core, we're not sure. We've never seen it, so we don't know. But very little of anything of interest is going on inside. The sphere is at a higher electrical potential, that's crucial, that is to say a higher voltage, than its surrounding plasma. The sun with the planets, the solar system, is sitting in this soup of plasma in our arm of the galaxy. And the sun serves as an anode and a cathodeless plasma discharge. A cathodeless plasma discharge is very simple to understand. Maybe some of you have even seen it. If you're a sailor like I was, you can talk about St. Elmo's fire at the masthead. If you think about a high voltage DC transmission line charged with hooked to the positive terminal of the generator on a foggy night, you might see a glow around that wire. What's happening is that the electrons in the high enough voltage, the electrons in the air, some of them are torn loose from their valence orbits and actually ionize the air particles. And so you get this glow discharge. It's a plasma discharge around that trolley wire, that transmission wire. Well, where do they come from? Where's the cathode? Is there a piece of steel out here someplace? No, it's a cathodeless. There's an anode, but infinity is where the cathode is. The photosphere is made up of anode tufts. I'll talk about that in a second. Little tufts, when you look at a plasma in the laboratory, in a plasma tube, if you look at the anode, if the current density is just right and the density, the pressure of the gas is just right, you can see these little dancing tufts on the anode. It's been a well-known phenomenon amongst electrical engineers for, well, since the days of Langmuir and before. The few neutrinos we do see coming from the sun are from nuclear reactions taking place. Wall and I sort of differ a little bit on this. I think somewhere in the photosphere or chromosphere. Wall thinks possibly in the penumbra of sunspots, although I don't think he excludes this possibility. But not at the center of the sun. The sun's corona is what we electrical engineers call a normal glow discharge. It's a plasma glow discharge. We'll talk a bit more about that. Here's one of my two sort of technical slides, and I had it on the other day. All three of these are radial distance away from the sun. The sun, you can think of it as a big ball over here. So we're traveling outward toward the right, radially outward from the sun. And that first top diagram obviously is the energy. That is to say, this is the voltage level. You can think of this as the potential hill. If you're a positive ion, and if you're in here in region B to C, you just sit there like a hockey puck on a frozen surface. If you get over here just to the left of point B, you're going to probably fall down that potential hill and fall back into the sun. In fact, any positive ion within the sun that wants to get out of the sun will have to climb that potential hill to get up to the top of that surface. If you're in random motion here, because it's fairly hot, about 6,000 Kelvin, as we said, so there's some Brownian motion, and your neighbor's liable to kick you over here near the edge, just to the right of point C. Then down the hill you fall. The second diagram is the force on any such positive particle. So obviously, if you're in region A to B and you're falling back down toward the left down the hill, yes, there's a negative force on you. Negative meaning the direction toward the left. So I hope it's a fairly explanatory diagram. And the bottom plot is the charge density, which gives rise to this E field plot and this energy plot up here. You don't necessarily have to concern yourself with this, except to realize that this is the so-called double sheath, a region of positive charge, and then followed by closely a region of negative charge. And that presents this sort of, what do they call it, an ogive curve or a reflex curve. Notice the steepest part of the hill is where the force on the positive ion throwing him out toward the right is the maximum. So clearly, what happens in such a case, if this indeed occurs, is that there's lots of thermal motion here, lots of temperature amongst the ions, but when they get over here, they're like a bunch of kids on a water slide. They get yanked by the scruff of the neck, and they fall very rapidly in increasing velocity down that water slide. And their attention is grabbed by the fact that they're falling and accelerating down that water slide, and they stop their Brownian motion. They become dethermalized. They're under such tremendous linear accelerating force that they stop that motion, and that's why there's a temperature minimum. And I've noted the temperature minimum at the point of maximum force, maximum acceleration. Whether it actually occurs there or a little bit earlier or a little bit late, I don't know. But it's somewhere in that neck of the woods. And that corresponds exactly with the observations that are inexplicable by the standard model of the temperature minimum. Notice by the time that you get out here to point E, the energy diagram doesn't go level, but it drops just a little bit. And that corresponds with a slightly positive E field. In other words, when the particles, the positive ions, get to here, they lose most of their accelerating force, but there's still a slight slope to the ice skating rink, and so they do go faster and faster and faster and faster. And that's why the solar wind accelerates. And so we've placed that double layer right in the chromosphere. Sorry for the misspelling, it's an M, chromosphere. And this horizontal, or in this case almost horizontal areas, both of these are what Langmuir would call true plasmas. The plasma can't support a voltage drop. Well, we claim there's a small one here, but and remember the other day, I hope you do, that I said that a double layer insulates or breaks up the plasma into compartments. And so the particles that are up here really are unaware of any particles down here, electrically unaware. No force, no pull, no nothing. Where the pull occurs is within the double layer. And so these positive ions are accelerated very fast here. If you're an electron coming in toward the sun, this is also a downhill slope for you, because what is an uphill climb for an electron is a downhill climb for a positive charge, and vice versa. And so electrons that come in here are, this thing, if you can think of it upside down, is sort of a trap for incoming electrons. And they actually fill up that energy trap, and eventually, if it fills up, it disappears. And that's the reason that the granules grow and shrink and disappear, and they're constantly in motion, growing, some more appearing, some disappearing. As they fill up with incoming electrons, they disappear. Well, anyway, that's the guts of it. I may come back. Maybe I've forgotten something about that. I alluded to this the other day, and that is that plasmas operate in 3 different modes: the dark current mode, the normal glow, and the arc. This graph is a plot of, if you think of a long cylindrical tube with an anode at one end and a cathode at the other, filled with some gas, and you strike an arc across there, we'll actually apply a positive voltage to the anode. You can get current to flow through that plasma. If the current density, if you control that current to a very low value, somewhere down in here, nothing's going to happen physically, or at least visually. You don't know anything's going on. You are getting there's some voltage drop across there, there is some current going through there, but it's not visible. So we call that the dark current. It looks like there's nothing going on. If you increase the current flow up to here, all of a sudden the thing lights up, and you get the typical neon sign kind of glow in there. The plasma glows. Now in that region there's all sorts of neat stuff that you can observe in a laboratory, the Crookes dark space and the columns and all sorts of interesting things. And finally, if you really increase the current density to a large current, instantly you jump into the so-called arc mode, which is like an arc welder or lightning. So what? Well, I maintain the following. If you can visualize, if you agree that the sun is powered by incoming electrons, or that there's a current going on there, if you think of the sun as something like a grapefruit here, and current coming into it or out, leaving it, electrons coming in, positive ions going out, which is a net current out, from that positive 10 billion volts. Think of a sphere, a very, very large imaginary sphere, way out beyond the orbit of Pluto, say. And think about the current density through 1 square meter of that sphere. If that sphere is way out there, there's a certain amount of amperes of current, but that sphere is so big that the current density, how many amps per square meter, are very low. Well, where does that put you? That puts you, if the current density, amps per square meter, is low, you're in the dark current region, and you can't see that you're in a plasma discharge at all. Well, okay, you start coming in, and you come into Neptune and Uranus and Saturn, Jupiter, and you get in finally closer than, say, Mercury, and all of a sudden the sphere is pretty small now, but the total amperes is the same. So the current density increases, and you jump into the normal glow. What's the normal glow? We call it the corona. And as you get in closer to the sun, and smaller and smaller and smaller, just above the surface of the sun, the same number of amps, but fewer square meters, so the current density increases yet again, and you're in the arc region, and we call that the photosphere. That's those tufts, those anode tufts that make up that granularization on the surface of the sun, which itself is a ball of gas at a certain voltage, and that's the anode. So, to sum it up, missing neutrinos, the missing neutrinos aren't missing, they're just not there. They're not there because the sun is not powered by thermonuclear fusion. Non-stationary convection, there's no need to convey energy out of the core because it isn't made in the core. The photosphere consists of tuft arc discharges, no matter what Eddington thought. Oscillation in the size and brightness. Those oscillations are due to two possible phenomena. The obvious one is that if the sun indeed is powered by those Birkeland currents, and they're twisty and therefore non-homogeneous, as the sun plummets through space, it's liable to go across those Birkeland currents and get more current, less current, more current, less current, more current, less current. Indeed, the sunspot cycle, as some of you probably know, is not really 11 years, it's 22 years. It's 11 years as far as the number of sunspots is concerned, but it's 22 years because on the second cycle, the magnetic field associated with the sunspots reverses. So it's really a 22-year cycle. How in the world are you going to explain that one from the fusion model? But if those Birkeland currents, as you go across them, if they're in different directions, or it's obvious that the polarity of the magnetic field can be reversed if the current reverses. And as you plummet through that snarl of Birkeland currents, it's possible for that to happen. So the way I think of it is it's a bumpy road produces vibrations. And those vibrations can be very high frequency. The second method is like a relaxation oscillator. And there are pulsars now that pulsate in milliseconds. And the typical astronomer's solution for that is, well, it's rotating and you've got a jet coming out, and as it comes around, as you see the jet, it's like a lighthouse. So it pulses. What, 24,000 RPM? That's pretty fast rotation. But as far as an electrical relaxation oscillator oscillating, that's low frequency. And that could happen especially if it's a binary star, because the discharge between the two stars can happen at a very rapid rate. The temperature minimum, I think that's the end of it for the Standard Model. I cannot see how anybody can propose a fusion reaction that has a temperature minimum. I mean, that breaks the law of thermodynamics. Heat doesn't flow uphill. And if there's a temperature minimum, how can it be? But with that dethermalization of the particles, they look like they're not less energetic. They just have less Brownian motion, so they look like they're less energetic. Acceleration of the solar wind, there's no explanation for acceleration of the solar wind. Acceleration of charged particles is exactly what you would expect if the sun indeed is at a higher voltage. There is an electric field, and you have a charged particle in that electric field. Of course it's going to accelerate. But how does the standard fusion model produce that? Well, what I forgot and I wanted to say in regard to the acceleration of the solar wind, I think I mentioned yesterday that on May 10th to 12th, 1999, the solar wind stopped. And what I wanted to tell you today was the quote that I looked up by a NASA scientist. I have his name, but I will remain anonymous out of mercy. He said, quote, "The May event provides unique conditions to test ideas about solar-terrestrial interactions. It also strengthens our belief that we're beginning to understand how the Sun-Earth connection works." Well, it sounds as though they become more and more convinced the more negative evidence they get. Well, what does this mean? The standard fusion model has many failures. It's continually being patched up. Every time a new phenomenon comes up, some new ad hoc explanation comes along. I would submit that the electric sun is simple. And by the way, that diagram of the energy diagram, the E field, and the charge density plot, those three plots, coincidentally happen to be exactly the same energy, voltage, and charge density plots that I taught for 35 years at the University of Massachusetts as how a PNP transistor works. And if you were interested in that, we can talk about that. And so the idea of controlling the collector current, which is the analogy of the solar wind, is a very simple thing. You just change the voltage level between the anode and the photosphere. And I wonder if that's what's going on and is controlling the solar wind. And you can indeed shut off the collector current in a PNP transistor, just like what happened on May 10th and 12th of last year. Consequences, I feel that heavy elements are not built up solely in supernova, as the docents at Kitt Peak are quick to tell you, but at the surface of all stars in the non-thermal compression and acceleration of plasma discharges, granulations. Hence, nucleosynthesis and what little neutrino production there is fall as the sunspot number increases. The differential rotation of the sun, its magnetic field, and the sunspot cycle are all influenced by the sun's passage across large Birkeland currents flowing along and defining the arms of our galaxy. And I didn't write that, Wall did, in Volume 1, Number 1 of Thoth. I will say, by the way, that another explanation for the sunspot cycle and the periodicities was written by an astronomer within the last year, and it went along, paraphrase it, the reason for the sun's memory is that a lump of magnetic field is somewhere caught down at the core. A lump of magnetic field. This person needs to take my E&M course. The parting thought I leave with you is the fairest way to deal with any problem is not to fall back on authority, what eminent authorities believe or don't believe, but to examine the evidence for yourself. And that's from Jeff Burbridge, Paulton's good friend and colleague. And I think it sets the tone for this entire conference, really. Thank you.